Welcome, everyone! In this lesson, we're looking at the cyber-physical built environment. That means buildings, infrastructure, sensors, digital models, and AI all working together. Instead of treating construction as a one-time project, we'll see it as a living system that can learn, adapt, and improve. As we move through the deck, pay attention to one big idea. Data is no longer just a report. It becomes part of how the built environment operates. Let's start with the problem. The AEC sector, architecture, engineering, and construction, has often worked in a straight line. Design, build, operate, repair. That sounds organized, but it creates silos. Information gets handed off, then lost or delayed. Construction 4.0 changes that by creating bi-directional data loops. In plain language, buildings send information back to designers, operators, and AI systems so decisions can improve continuously, not just after something breaks. Now let's define the 4 scales of a digital twin. A component twin tracks one part, like a pipe or structural element. An asset twin represents a larger object, such as a bridge. A system twin connects flows, sensors, and utilities. A process twin follows construction activities like scheduling and logistics. This hierarchy matters because each scale answers a different question. Is this part healthy? Is this asset safe? Is this system efficient? Is this process on track? Here's a key distinction to remember. BIM and digital twins are not the same thing. BIM, or Building Information Modeling, is mostly static and design-focused. It helps coordinate geometry, structure, and construction intent. A digital twin is dynamic. It uses live sensor streams, cloud tools, IoT platforms, and machine learning. Why does this matter? Because BIM helps us design and build, while digital twins help us operate, predict, and optimize over the building's life. This slide shows digital twin maturity as a staircase. Level 1 is descriptive. A static model works like a record. Level 2 becomes informative with live sensor data. Level 3 is predictive, using context to forecast failures. Level 4 is comprehensive, running simulations. Level 5 is autonomous, where closed-loop controls adjust systems with little human intervention. The important takeaway is that maturity increases as the twin moves from documentation to prediction and finally to action. Now we add the cognitive engine. Think of this as the brain inside the digital twin. Live telemetry feeds AI models that predict problems, optimize controls, and explain what is happening. Large language model interfaces make the system easier to use, letting managers ask questions in natural language. The minimum viable twin, or MVT, is also important. It means we should avoid unnecessary complexity and model only what the AI actually needs to solve the task. Here we see a practical example: autonomous HVAC control. HVAC systems must balance comfort, energy use, and cost. The predicted mean vote, or PMV, measures comfort, aiming near neutral. The predicted percentage of dissatisfied, or PPD, should stay low, ideally below 10%. Multi-objective algorithms evaluate these goals together. This matters because comfort and efficiency often compete. A smart system does not simply save energy. It saves energy while keeping people comfortable. Data is powerful, but only if systems can actually understand each other. This slide is about interoperability, which means different tools can exchange and interpret information. The semantic data stack transforms static 3D geometry into queryable knowledge. Industry foundation classes, scripts, semantic parsing, relational tables, and knowledge graphs all help connect meaning to building data. Why does this matter? Without shared data structure, organizations get trapped in vendor lock-in and disconnected digital models. Reality capture brings the physical site into the digital workflow. Low-cost 360 cameras and drones collect visual information quickly. AI photogrammetry turns raw images into a point cloud, which is a digital reconstruction of actual site conditions. Then, automated auditing compares that reality against the 4D schedule, which combines the model with time. This matters because teams can identify delays, confirm completed work, and reduce disputes before small problems become expensive surprises. This proof point shows predictive health at Smart Bridge Hamburg. The asset carries thousands of vehicles daily, so structural insight is critical. Instead of waiting for visible damage, the bridge uses hundreds of IoT sensors to monitor strain, temperature, acceleration, and displacement. AI then creates a simulation sandbox where extreme traffic scenarios can be tested virtually. The big idea is prevention. A digital twin helps engineers see stress patterns before physical failure occurs. This slide looks ahead. Human-centric monitoring tracks physiological signals like heart rate, skin conductance, and wearable cognitive load. The goal is not surveillance for its own sake, but safer scheduling, fatigue prediction, and better worker support. Blockchain verification appears on the other side, helping secure modular prefabrication records, assembly metrics, and smart contract payments. Together, these ideas shift construction from just managing materials to managing trust, safety, and verified performance. Safety training becomes very different when synthetic environments are involved. Here, tools like NVIDIA Omniverse and Dassault systems generate realistic virtual construction sites. These synthetic scenes can include unsafe behaviors, such as missing personal protective equipment. AI vision models train on that data, then deploy to real cameras on physical job sites. Why does this matter? Because the system can learn rare but dangerous situations before they happen around real workers. This slide looks ahead. Human-centric monitoring tracks physiological signals like heart rate, skin conductance, and wearable cognitive load. The goal is not surveillance for its own sake, but safer scheduling, fatigue prediction, and better worker support. Blockchain verification appears on the other side, helping secure modular prefabrication records, assembly metrics, and smart contract payments. Together, these ideas shift construction from just managing materials to managing trust, safety, and verified performance. Here is where the numbers make the case. The slide highlights major savings: hundreds of thousands in direct construction cost savings, millions in avoided retrofitting costs, major electricity reductions, and post-construction energy savings. These metrics matter because digital twins must prove value, not just sound futuristic. When accurate models identify vulnerabilities, optimize operations, or reduce energy use, the business case becomes clear. Better data can directly reduce cost, risk, and waste. Let's close with a central message. The future built environment depends on data as a core competency. That means firms must treat data as a continuous lifecycle asset, not a byproduct of design. By moving beyond proprietary silos toward interoperable standards and cognitive AI, the industry can bridge static design and autonomous operation. The result is a built environment that reduces operating costs, improves worker safety, and supports resilient Construction 4.0 systems.